All right, so when we're looking at these ones here, we're going to look at the limit, but we're going to do it from a different approach here. We're going to look at algebraically, okay? Which means we're going to take away the graphs even more, right? All right, find those following limits, guys. The limit of f of x as x approaches 2. So as x approaches 2, if it doesn't specify a side, it means from both sides. Here's 2, go find 2, approach it. Am I? All right, sorry about that. There you go. Good? So as we approach it from both sides, what number am I approaching, Tomas? 3. Awesome. Next one. Well, because what we drew, right? We go find 2, we go up to the function, we approach it from the left, we approach it from the right, and in both cases, we're approaching that point there at 3. The limit as x approaches 1, so now we're going to look at 1. 1 is this asymptote. What are we approaching from the left-hand side? Negative infinity. No, you're up and downs, boys. And from the right, positive infinity. If the left side and right side are different, what does that mean? Does not exist. Not one, Raquel. Left side does not equal right side. Okay? If you want to be even more specific, you could say negative infinity does not equal infinity. Right? Show that they're both not the same thing. All right. Make sense? Any questions about those? Or are we good? We're good? All right. Guys, when we talk about infinities, just make sure that we specify whether it's positive or negative, all right? Because it's happening a lot. Not just like audibly, but also like in the work when I look at your guys' work. So, all right. Moving on. Consider the function 1/2 negative 2x plus 4, absolute value, minus 4. The graph of f of x is pictured there. From the graph, let's determine the following limits, okay? So we're going to find f of a using the equation, meaning I'm going to plug in like what a is. A is the value that x is approaching. So in this case, it's 0. So I'm going to plug in 0 here. Negative 2 times 0? 0. Yeah. So actually, let's write it out. It'll be easier if we write it out, I think. So negative 2 times 0 plus 4. All right. So I got negative 2 times 0 plus 4, which is? What's 0 plus 4, guys? 4, there we go. Absolute value? Still 4, right? Doesn't change sign. Times 1/2? 2, right? So this whole part here simplifies to be just 2 minus 4 or negative 2. Okay?
So the lines are individual.
The lines here? No, those lines mean absolute value. So if it was a negative value, we'd flip it to be positive. Okay? That's all it means. Is that what you're asking? Okay. So now let's look at the actual graph. Let's look at it. So as we approach 0, here's 0 on my graph. From the left and from the right, what number am I approaching? Negative 2, the same value, right? I'm approaching the same y value of negative 2. All right, let's do the next one in another color so it's easy to see. This time, I'm going to be approaching 2. Does the positive side matter when I'm just plugging it into the equation? Not technically, right? Like there is a chance that it could matter because of these absolute values, but you're going to see in this case it's not going to make a difference. So we're going to get 1/2 times the absolute value of negative 2 times 2 plus 4, absolute value, minus 4. What's negative 2 times 2? Negative 4. What's negative 4 plus 4? 0. And what's the absolute value of 0? Still 0, right? And then 0 times 1/2? Still 0. We like it when we get zeros, right? So we literally have 0 minus 4 or negative 4. Now, let's see if that's what we get when we do the limit of it, right? So we're going to look at our graph. We're going to go to 2. We're going to go to the positive side of 2, and then we're going to trace it down to the value of 2.
Why are we talking about absolute values as well?
Why not? It's all fair game. It's all pre-calc. Guys, I'm going to throw stuff at you from pre-calc all the time, because the whole point is that we should know. Go tell, guys, absolute values you learned in like grade 9 and grade 8, so it's not Sandra's fault. Okay? Absolute values you learned in middle school and in Algebra 1. That's when you first learned them. Doesn't mean you didn't use them last year. You might have, but anyway, that's not when you learned them. Yeah.
question, what is that equation like represent? Like what is that 1/2 and what is that 1/4? Like that represents that function, right?
This here is just a function. It doesn't tell us that it represents something specific. It's just like there's no context given, right? I'll give you guys word problems. Do you want them already? That's what I thought. Okay, so as we go to the right-hand side of 2 and we approach 2, what y value am I getting to here? -4, right? So the limit was -4. Now, this is kind of important because what this is telling us is that when a function is defined and continuous at a value, then x equals a, then how can the limit as x approaches a of f of x be found analytically? Well, let's first start and make sure you guys remember what continuity means. You guys remember what continuous means? What does continuous mean? You don't need to draw this unless you don't remember what it is. What's continuous? Nobody remembers. Oh, God. Guys, we've already talked about continuity. Continuous means we can draw the graph without lifting our pencil. You guys remember that now? Does that sound familiar? Yeah? We're going to get into more interesting definitions later, but for now, that works for us. Okay? Now, how can we find that limit analytically if it's continuous? Well, look at the 2 examples we just did. Did we get a different answer when we took the limit versus plugging it into the equation? Or did we get the same answer? Look at what we did. Are they the same or are they different, guys? Are the values different when we took the limit, this was the side with the limit, versus when we plugged them in? They're the same. So in other words, if this is continuous, what we can do is we know, student blue, f of a is equal to the limit as x approaches a of f of x if f of x is continuous, which we've kind of already hinted at some of our questions. Remember the question from your homework where you had to tell me if the limit existed between -1 and 1 for all values of c? I know some of you did it because you came and asked me about it. Do you remember that question from your homework? Guess I'm going to have to do a homework check. What do you mean it's so hard? This is actually the easy part. This is saying, like, if the function's continuous, we don't even have to do calculus. We can just plug it in and we know what the value is. So in other words, what we're learning is the very first thing we should try with a limit is what? Plug it in. Just plug it in and see if it works. If it doesn't work, that's when we're going to have to maybe do something interesting. Yeah.
How do we know it doesn't work?
Because you divide by 0, right? Or you get like the square root of something negative. There'd be some reason that it's undefined. If it's undefined, then we got to do something. Because remember, the function can be undefined and the limit can exist. So the first thing we can always do is just plug it in, see if it works. If it doesn't work, now we got to do something. Okay? Yep. I don't know, man. The fact that you asked, maybe it's closed. You should take a lot of notes. It'll be closed. Yeah, it actually is closed. All right. So let's find these limits then analytically. So remember, the very first thing we're going to try, so let's do this, guys. I want you to put like a star up here and say, first, try plugging it in. Okay? And then basically what we need to know is like, if that doesn't work, then we got to try something else. Okay? So the very first thing I'm going to try on this first one is just plug in what value for x? 3. That's all I'm going to do. Okay? And if I plug in the value, I don't even need to write limit anymore. So I can just literally say equals 1/2 times 3 squared minus 2 times 3 plus 3. This should feel like pre-calc at this point, right? Then I work it out. 3 squared is 9. So we got 9/2 minus 2 times 3. -2 times 3. -6. Good. Then I can put those together. What's -6 plus 3? Good. So we got 9/2 minus 3. How do I put those together? Common denominator. Great. So I'm going to, exactly, you got it, Raquel. And then finally, I'll get 3 halves. Okay, so the limit is just 3 halves. Why? Because it's continuous and that's the function. Because 9 minus 6. See, you should listen to Raquel. Look at her. She knows stuff today. That's perfect. That's great. All right, let's look at the next one here. Okay? So basically, we need to know if it's continuous because then we can just plug it in. Is there a value here that's going to make this thing not continuous? What do you guys think? Huh? Maybe? Yeah, maybe. What would make it discontinuous if the bottom is what? Not negative. Bottom could be negative. 0. So if 2x minus 3 is 0, we'd have a problem, which would mean x needs to be 3 halves. Are we approaching 3 halves? So we're fine, right? We know we can just plug it in. So let's go ahead and do that. So this is just going to be 5 times 3 plus 2 over 2 times 3 minus 3. Then we just simplify that. 5 times 3, 15 plus 2. 2 times 3, 6 minus 3. What's 15 plus 2? 17. What's 6 minus 3? There you go. See, you did another one. Look at you.
But it's easy to
So this part,
erase all of this and then
so
again.
all of these parts, those,
I mean, we'll have some harder ones, yeah. But for now, we're good, right?
this part is just changing.
Well, because what you're gonna, that's why basically we're using this rule, right? Like the first thing we do is try plugging it in. Because the only time, guys, that we can't just plug it in is if it's undefined. So as long as the function's defined and continuous, we're okay. All right.
How do you know if it's continuous?
How do I know? That's where I got to rely on my precalc. So for instance, if we look at a function like this first one, polynomial. Are polynomials continuous everywhere? Is there any way I can make a polynomial undefined? Maxo. So what does a quadratic look like, guys? Something that's squared. What does that look like? If I have x squared. Parabola, right? It literally just looks like this or like this. And I can stretch it and move it around, but that's what it looks like. That's a quadratic, buddy. If you don't know that, you're going to have to go back and bug your grade 9 teacher. Okay? Actually, for you, it's probably your grade 8 teacher. No, it's just that's what a quadratic is, right? So if it's a quadratic, is there anywhere that a u is not going to be defined? Is there any x value that it can't be?
Yeah, negatives.
No, it could be negative. There's y values it can't be.
Yeah, that's
So that's what you're thinking. Remember, guys, we're talking about like the domain. So this way, is there any value it cannot be horizontally? No, it could be everything, right? When you defined these, Maxo, guys, what was the domain of a parabola?
Give an example if it was discontinuous.
Oh, I'm going to. Okay, so for instance, if we graph this and take a look at it, sorry, that's some ape stuff for you. What's the function again? Read it to me. It was like 1/2 x squared. 1/2 x squared, then what? Huh? Minus 2x plus 3. So if we look at this, and I zoom out here, guys, right? Like, it exists everywhere. There's nowhere that's not existing. It might take a long time to get somewhere, but it's going to get there. Okay? Now, what was the next one that we had?
5x plus 2 over 2x minus 3.
Over what?
2x minus 3.
Maxwell, Jose, I'm going to kick you guys out in about 10 seconds, guys. I did, thanks. There we go. So here, there is a value you can see here where it's not going to exist, right? There's like this line here where this thing doesn't seem to exist. And if I scroll out, it becomes even more obvious. What is there right here? What is that value going to be? What's it called? An asymptote, right? And specifically, that asymptote lives here. Do you see how that function is getting close to that asymptote without touching it? How did I find the asymptote? I made this equal to 0, right? So I add 3, divide by 2, that gives me my 3 halves. Okay, so that's an example of one that's undefined. All right? If you look at the next one, what was it? It was like square root of 2x something. What's All right, what was it? Square root of 2x?
No, that's 2x. It's x plus 2x.
X plus 2,
Over x plus 1.
like that? Okay.
No, you beat the minus 1.
Oh, this is like minus 1 at the end of everything? Like that?
No. But we have that square root.
Okay, but not inside the square root. Okay, cool. So then we get something that looks like this. You can see very clearly, like this function will not exist when x is less than negative 2. If you look at that, why would that be? What is it about this thing here that's going to make it not exist when x is less than negative 2? The square root, right? I can't take the square root of a negative number. If x is less than negative 2, let's say negative 5, Maxo, what is it? Guys, I'm going to split up your table like really close. Really soon, guys, okay? Yeah, if I plug in something like negative 5 plus 2 is? Negative 3. What's the square root of negative 3? Oh, I can't do it, right? It's negative. Well, he's not completely off if he uses imaginary numbers, guys. I don't know if you learned those, but I don't know why you learned them, because you shouldn't, but you don't need them till university. Most of you in here, like unless any of you guys are going into like engineering, physics, something, you're not even going to use them ever in your life. So it's stupid that you learn them. They're not hard, they're just not something you need. Yeah, they're super easy, they're just not something you need. Okay, so let's see, where were we now? Oh man. Oh, it won't even let me switch my screens. No good, no good. No, the point is I want to be able to like get to my other tab and I can't. Because it won't let me select it. Oh, really? There we go, perfect. All right, so we know that this one has a problem. Where's the other place that this one has a problem actually? If we go back and we look at this, where's the other place that this is going to have a problem? At what value? Yeah, what'd you say? X minus 1. If I look on here, guess what happens when I go to minus 1? If I can get there. It won't let me. Come on. It literally is not going to. There we go. What does that say? Undefined, right? Now, obviously, that means that we could cancel it out. So it's a point of discontinuity, not an asymptote, but it still doesn't work. Well, if you don't have a graph, you just look at these, right? We know that if the denominator is 0, it's a problem. And we know that if a square root is negative, it's a problem. So in this case, the two values that are going to be problems are negative 1 or anything less than negative 2. No, there would be a problem. So in this case, if we're approaching 2, is there a problem? Exactly. So if there's not a problem, we can just plug it in, right? So let's do that. The square root of 2 plus 2 minus 1 on the outside over 2 plus 1.
But does that negative affect?
This one? Not in this case. It would if it was at like negative 2. If we were approaching negative 2 from the left, what would that mean? That we'd be approaching something less than negative 2. Can we do that? No. So then it would be a problem. All right. What's the square root of 2 plus 2, or the square root of 4? So we got 2 minus 1 over 2 plus 1, which is 3, which is really just 1/3. Exactly. Now, I know you guys don't like trig very much, but if you think about trig for a minute, is there any value that a trigonometric function, sine or cosine, are ever undefined? Tangent, yes, you're right. Tangent has a whole bunch of values, absolutely. But sine and cosine, it's just a wave that looks like this, right? If you remember from physics or chemistry, I don't know. I don't know when you guys learned it. You should have learned it. It literally is just a line that looks like this, right? It's just a wave. So that means it's defined everywhere. So there's no value we can put in here that's a problem. Tangent, there is. Sine, there isn't. So we can just go ahead and plug it in. So sine of 2 pi over 2. What happens to those 2's? They cancel. So I'm going to get the sine of pi. Luciana, look at the unit circle over there. Tell me what sine of pi is. Sine of pi. So find pi, and sine is the second number. It is 0. Luciana, do you see why it's 0?
I don't like 5.
Maxo, can you show everyone?
0 because it's in the y.
Yeah, exactly. Because sine is the y, so sine of pi, or the y value of pi, is 0. So this thing just equals 0. Okay? I guess I could put the answers up here too. What does that mean? It means it's 0. No, it's just 0. There's no problem. It just means it's 0. It's going through the x-axis. All right. Now let's find these ones. So what we're going to do here is we're going to plug them in and kind of check them all. That one was, yep. So I'm going to plug in -3 here. -3 squared is 9. -3 times 4 is -12 plus 3. What does that equal? 9 minus 12 plus 3. 0, which is not a problem if it's on top. On the bottom, -3 squared is 9. -3 times 2 is -6. Minus 3, what is that? No. 9 minus 6 minus 3, it's 0. Is that a problem? Yeah, we can't have 0 on the bottom, right? So this one's got problems. Right? What I'm doing is remember the first thing we did, we said, is just plug it in, right? So my first step, guys, remember, first step, just plug it in, right? Then, if there are problems, undefined, we need to do algebra. So that's what we're going to get to here, is we're going to show you what happens when we can't just plug it in. Okay? So this one here, now I'm approaching 1. Okay? If I plug in 1, do I actually care about the numerator at all? I actually don't, right? Because that can't give me a problem. The only thing that can give me a problem is the denominator. So now let's just check that one. So 1 squared is 1. 2 times 1 is 2. Minus 3 is 0. So again, we've got problems. Now, if we approach it from the right side, is it going to be any difference if we're just plugging it in? In this case, yes. This one here, it's going to be the same, right? It's going to be 1 plus 2 minus 3 equals 0, because it's just approaching 1 again. So all of these have problems for us, right? Yeah, we're just checking the denominator, because if the numerator is 0, it actually doesn't matter. What matters is if the denominator is. Okay? They all have problems, which means I'm going to show you what to do when we have problems. Okay? So if we look at the next part here, we're going to actually see a graph so that we can, again, help us understand it. Okay, so here, if you look, these are the exact same 3 limits, right? Exact same 3 limits. But previously we said, oh, it didn't work. There's problems. And you might think, oh, it's undefined. But that's not the case for the limit. Remember, the limit can be different. Lucas, wake up, buddy. Okay? All right. So what I'm going to do first is approach -3. -3 is this hole. From both sides, I am approaching the same value, and it tells me where that hole is. What am I approaching? -3, but what's the y value? 1/2. So the limit does exist, and it's 1/2. So even though the function doesn't exist, the limit does, right? So then we're going to have to figure out how can we look at this algebraically, which we'll do next. So now let's look at 1. 1, we can see here, is the vertical asymptote. So we're going to approach it from the left, which would be here, and I'm plunging down to what? -infinity. Okay? And then on the right-hand side, right, so I go a little bit to the right of 1. That's okay. Raquel, no worries. So I'm going to 1, right? This is 1. I go a little bit to the left because it wants me to approach it from the left. And then I trace the graph back towards 1. And I'm going way down to -infinity. If we do the same thing from the right, I find 1, I move to the right, I find the graph, and I trace it back towards 1. And what am I doing this time? Positive infinity. What's up?
How do I know if it goes down?
Okay, so what you have to remember, you guys, is how you're approaching it. So if I'm approaching it from the left, that actually means I'm moving right. Right? Does that make sense? Think about it this way. Tomas, come stand in the middle of the room. No, really, come stand in the middle of the room. He's talking, so we're going to use him as a guinea pig.
Here, middle.
Right here. Right up here in front. Okay? What side of Tomas am I on? I'm on his right, right? So if I'm approaching him from the right, which direction do I move?
Right. Left.
I've got to move which way? This way or this way to get
You're
to him?
confusing me more.
I'm confusing you more. Really?
I didn't know.
Am I on his right? I think the problem is you guys don't know right.
Then I
No, what's that? Okay, face this way. Face this way. Which side of him am I on?
Left.
The left. So if I'm approaching him from the left, which direction do I move? Right. Okay. If I am approaching him from the left and I move left, I'm going to go this way and get further away from him. That's the part that's a little bit confusing, right? If I'm approaching from the left, I move right. Okay? So you can go sit down. Yeah. So here, if I'm approaching from the left, I have to go to the left-hand side and then move right. As I move right, I get down to negative infinity.
how do you know you need to like not go up, for example, to that point? and
Well, because if I went this way, then I'm not moving towards 1. I have to approach 1. So I have to move towards x equals 1. Okay? On the right side, same thing. I have to move left because I have to get closer to 1. All right? Now, before I go any further, in this case here, what does that mean about the limit as x approaches 1 of f of x, guys? Does that exist or not?
No, because they are
Exactly.
different.
Exactly. They do not exist because the left side didn't equal the right side. Okay? So just to refresh our minds on that. Okay. So now we have to determine how can we find these limits analytically. If we didn't have the graph, what would we do? So how did you find discontinuities in a rational function in pre-calc or in algebra 2? You factored them. Exactly. Right? We had to factor. So that's exactly what we're going to do here. We're going to take that function and we're going to factor it. Right? So, I don't know. How good are you guys at factoring? All right, good. Let's factor the top. What is the top there? Good. So the limit as x approaches negative 3 of x plus 3, x plus 1. Guys, if you don't know how to get to that, you should come see me later, okay? And I can walk you through it.
Where did you get that?
From factoring, which you've been doing for a few years. So that's with it. All right, guys, let's look real quick, real quick refresher. I'm looking, just wait. I'm looking for something that multiplies to a, which is 1, times c, the last term, so 3. I'm looking for something that adds always
So the bottom
to
one
b,
would be
which is 4. So in my case, the only two numbers that multiply to 3 and add to 4 are 3 and 1. On the bottom, I need to multiply to negative 3, and I need to add to 2. What two numbers do that?
x plus 3 and x minus 1.
Exactly. So this is going to be x minus 3, sorry, x plus 3, my bad, and x minus 1, right? Because those two numbers multiply to negative 3 and add to 2. If you're having a hard time with that, guys, you got to come see me later.
So I have a question about that.
Okay?
What if it's flipped like negative 3, positive 1? What acaba?
Then we would cross out the ones.
Yeah, but like why aren't we using?
Because you can't. Because negative 3 and positive 1 would add to negative 2, not positive 2. Right? That's why it had. Yeah, exactly. You're adding. So we have to add to positive 2. Okay, so let's cross those out. Now that's important because when I cross those out, guys, what did I just cross out? I crossed out, yeah, the thing that's going to be the whole. No. Because now, did I get rid of the problem? Can I plug in negative 3? Absolutely. So now I can just go, once I've simplified, I can go right back to my first step. Plug it in.
Mister, it's the first one has to multiply it and equals 3 and then add it and equals 1.
Yep. Well, in this case, no, it was add to,
Subtract with.
this case it was add to 2 or add to 4, depending.
I didn't.
Guys, once I've done the simplification, I just plug it in again. Go back to step 1, plug it in. So I get negative 2 over negative 4, which is really, what's negative 2 over negative 4? 1/2, right? Negatives cancel. Negative divided by the negative. All right, so that means then, based on our knowledge from pre-calculus, when a rational function has a non-removable infinite discontinuity, so in other words, you couldn't cross it out, what did you end up getting? What was it called when you had something on the bottom that you couldn't get rid of? Instead of a hole, what'd you get? What's an asymptote? It's just an asymptote, right? Okay? Since the y values do not approach one specific values from both sides at an asymptote, then the limit does not exist. And that's what happened at 1, right? 1 was our asymptote, and we got negative infinity and infinity. No limit, okay? But we can determine if the one-sided limit approaches negative infinity or infinity, okay? So the way that we can do that is by doing a little bit of analytics, let's say. So we know that our simplified function became this, right? X plus 1 over x minus 1. That's why we knew that 1 was an asymptote, because we couldn't get rid of the 1 on the bottom, and 1 minus 1 is 0, okay? That's how we knew it was an asymptote. So here's what we're going to do. At that point, if we're approaching an asymptote, what are the only two things we can approach? What do we have to do? If I'm heading like this, what's the only thing I can do?
Left or right? No,
Yeah, well, but like vertically. So I have to go down or up. So I'm going to infinity or negative infinity. There's no other options. So all I need to do is figure out which one, which means that I can do like a sign analysis because I already know where I'm headed.
Sure, can that function just stop?
Huh?
Like, you have to go forever. Or like, it just stop?
It can, but usually won't unless we restrict it for some reason. That gets more into like word problems. Okay?
So it's going to be negative or
It's going to be negative or positive infinity, yeah. Okay, so looking here, I'm going to pick something to the left of 1. To the left of 1 would be like 0.1. Would you agree? Good. Remember, all I care about is the sign, so I'm not going to work out what the actual value is. If I have 0.9 plus 1, is that positive or negative? And if I have 0.9 minus 1, is that positive or negative? What's a positive divided by negative? So this is going to approach negative infinity, which it did. Remember, we already did this. Okay? Do you understand why I'm just looking at the sign? Because I know it's going to infinity. I just need to know positive or negative infinity. So now I'm going to put something to the right. 1.1. 1.1 plus 1, that's positive. 1.1 minus 1, that's also positive. What's a positive divided by a positive? So this is going to go to positive infinity. Yep. I mean, arguably, yes. The problem is what happens if that whole number in a piecewise function puts you into like a different function. So it's better to pick something like just one decimal off. Mara, stop shopping. What did you ask for, Cal? So all I'm doing is I'm just looking, like this is just the sign. I know I'm going to infinity, so I just want to know which one. So I'm looking at 0.9 plus 1 is positive, 0.9 minus 1 is negative. And if I divide a positive by a negative, I'm going to go to negative, which means it's negative infinity.
So why that second one is not the same?
Because here I'm putting in 1.1, something to the right. 1.1 plus 1 is positive. 1.1 minus 1 is still positive. Okay? No, man. One more page. Last page. All right. So, I don't know how good you guys are at finding out functions. So I'll give you them. All right. So this function here is negative x minus 5. Okay, that's this first one here. And that line only exists when x is less than negative 3, right? So that's me highlighting this line. Do you guys all see that? Does that make sense? All right. Let's do the other line next. So that line is only going to exist when x is bigger than 2. And that function is going to be negative 1/2 x minus 1. Okay? If you don't remember how to do that, don't worry about it. Okay, usually we're going to give them to you. I'm just doing this to help you. That's this line. Now I'm going to do the quadratic in the middle. And that one's going to be x plus 1 all squared minus 6. And that one exists from
y-intercept is 5. No, 6.
No, the y-intercept is -5, but the function is this. Because remember, this is when you completed the square in pre-calc, and you did it because this gave you the vertex, and my vertex is at -1, -6. So x minus -1 is x plus 1 minus 6. Okay, so it's a special way of writing them that makes it easy to find them. That's why. Okay. Now that we have those, we've got the graph as kind of a support, but we're going to use these functions because the whole point is to be able to do this eventually without functions, right? So we're going to use the equation to find these limits rather than the graph, okay? So the limit as x approaches 2 from the right. If I look up here, which one of these functions are like domains is x to the right of 2? So bigger than 2. The last one. So that means that I'm going to plug in 2 into the last function, right? So this is going to be 1/2 times 2. Wait, it was -1/2? Thanks, okay, thanks. -1/2 times 2 minus 1, which is, what's -1/2 times 2? -1? Negative, because it was negative, right? But it is 1, you're right. And then -1 minus 1? Oh, we have 2 negatives, so it's -2. Yeah, because we have a negative and we're subtracting another, like we can't do that. We're subtracting a positive or adding a negative. All right, so we got -2. All right, let's go look at the graph and see if we're right. Okay, as we approach 2 over here, from the right-hand side, did I indeed get to -2?
Yes.
So you see how we can use the function and the domain to figure out how to get these? Does that make a little bit of sense there? Yes? Okay. So let's try the next one here. This is the limit as x approaches 2. Now this is where it's a little bit trickier, right? Because if it's approaching 2, I need both sides. So we already did the right side. So this needs to be split up into the limit as x approaches 2 from the left. And what was that one? That one was the -1/2 x minus 1. And it needs to be equal to the right side. So I'll write left side, right side on here to help you out. As x approaches 2 from the right, what's the function that was in the middle again? I think it's like x plus 1 squared minus 6. Thank you. So do you see why I need to do both this time?
Yes.
Because I need the left and right side to be equal. Now, luckily, we did the left side. It's already -2, so we don't have to worry about that one. The right side, we need to do. So let's plug it in. 2 plus 1 squared minus 6. 2 plus 1 is 3 squared is 9. And 9 minus 6 is?
Did you get that?
This equation? Because if I'm trying to go from the left side of 2, this middle function here is the one that's on the left side, right? Because this is saying x is less than 2. So I have to use this function for the, oh, I wrote it backwards. That's what's confusing, isn't it? Yeah, I wrote that backwards, sorry. This should have been the right side. This is the left side. Is that what was confusing you, Raquel?
No.
No?
Didn't you?
You didn't? No, okay, well, I did write it backwards, guys. I apologize. No, wait, did I? Oh, I wrote the symbols wrong. Yeah, this should be like the right side, so positive, left side, so negative. Yeah, so I did write it wrong. Okay. And what's 9 minus 6? 9 minus 6 is 2? It's 3. Do those things equal? No. And if they don't equal, we can say that this thing does not exist because the left side does not equal the right side. Right? 3 does not equal -2. Okay? So we can do that algebraically. Let's look at the graph and make sure it's right. If you look up at the graph and you approach 2, do you indeed get 3 and -2? So you're still writing this, so I don't want to scroll up. If you look at your graph, are you approaching 2 different numbers? Yeah. Therefore, it doesn't exist. Right? So I'm going to scroll up for a second. If you're not quite done, just bear with me. Right? We already did that from the left side, or sorry, from the right side, we got -2. And from the left side, we did indeed get to 3. So it doesn't exist.
So a question.
Yep.
If in that case there is a graph, can we just write the answer?
If there's a graph,
Can we just like write the answer?
yes, of course. If it's multiple choice, yes. If it's written, you need to write down some stuff. So the next two here is we're going to look at -3 and -3, right? We're going to look at the two sides here. So let's see how good you guys are at this. If I'm approaching -3 from the left, which of these three functions do I need? What is smaller than -3? What?
No.
Which one of them is smaller than -3? This one is when it's bigger than 2. This one's between -3 and 2. Exactly, Martine. This one is when it's less than -3. So I got to use this function here, right? So this is going to be, when I plug it in, it's -3. I already forgot the function. -3 minus 5, right? So that's 3 minus 5, which is -2. So the answer is just -2. Okay? It's that easy. The hardest part about this, guys, is figuring out which equation to use, honestly. So now, if I'm looking at -3 from the right side, which function do I use? So let's scroll up. Which one of these has x being bigger than -3? The second one, right? Now, technically, this one is 2, but not really, because this is saying it's bigger than 2. So this is like more restricted. So we got to use this middle one, right? What's up, Raquel? Because that's the boundary points, right? Here, this is at -3. Here, this is at 2. And that's where the three different functions came from. All right, so we got to use that middle one, which is, it was x, so -3 plus 1 squared minus 6. Okay, then I worked that out. -3 plus 1? -2 squared? 4, good. 4 minus 6 is also -2. So as an extension question, does the limit exist at -3? Yes, because the left side and right side are equal.
Sir, for example, that you will put us a lot of problems that you don't know, you don't specify if it's from left or right, we have to cover both.
Yeah, I will give you some. Yeah, I'll give you some like that. Yeah. All right, now let's look at this. The limit as x approaches -7. So that means both sides. So if I'm at -7, which of these three functions do I need to use? Where is x less than? This one? That says x is bigger than 2. So it can't be that one. First one, right? X is less than -3.
But for the circle.
Maybe I'll have to check. So -7, is it only here?
No, it just is the one that it like touches. Like,
Yeah, like in this case, it's only going to be -7 because it's not a boundary point. I only have to use this particular function. There's only one function at -7. So this is going to be -7 minus 5, which is 7 minus 5, or 2, right? Now, let's go look at the graph and confirm like we've been doing. Okay? So if I look at the graph, at -7, I go to my graph, right? As I approach it from the left and right, well, it's continuous, so I don't even really need to worry about it. It is definitely 2. Does that make sense? Yeah? Any questions about it? No? All right, last one. Last one. Limit as x approaches -1. So again, both sides. So we're approaching -1. Which one of these three is -1 going to lie in the domain? The first one would be less than -3, so it can't be that one. Is -1 bigger than 2? No. Is -1 less than -3? No, so it has to be here, right? Between -3 and 2. So I'm using the middle one. So this is going to be -1 plus 1 squared minus 6. What's -1 plus 1? 0. 0 squared? 0. So it's just 0 minus 6 or -6. Okay? Kind of makes sense? Hopefully. Awesome. All right, guys. After that, it is just the practice problems. You do still have 17 minutes, so you can probably get a good chunk, if not all of them done. Okay?